On this channel, we provide useful programming information with practical code examples. This time, we'll focus on synchronization control in Python asynchronous processing. You will learn step by step, from the basics of asyncio to practical patterns commonly used for synchronization control. Enabling subtitles will make the code descriptions easier to understand. In asynchronous processing, you can easily run multiple tasks simultaneously. However, in practice, more advanced adjustments are required, such as controlling concurrency, coordinating tasks, exclusive control of shared resources, handling heavy synchronous processes, and cleanup after cancellations. Here, we will learn step by step from the basics of asyncio to practical patterns commonly used for synchronization. Let's first look at some minimal asynchronous code. Await waits at that point until the called coroutine completes, and asyncio create_task schedules a task for concurrent execution. This code is a typical pattern where tasks are explicitly created, run in parallel, and the results are received at the end with await. Create_task enables concurrent execution. When running multiple coroutines concurrently, you choose which to use depending on how you want to retrieve results. Gather waits for all to finish and returns the results in input order, while asCompleted allows processing results as they complete, regardless of order. As shown in this code, gather returns results in input order, making it useful when you want to preserve order. asCompleted is used when you want to process results as soon as they finish. When there are external API rate limits or DB connection limits, you can control concurrent executions with a semaphore. By using semaphore with async with, you can easily limit the number of simultaneous executions. This is effective in situations with external constraints. Lock is used to prevent simultaneous updates to shared data. Asyncio.Lock is an exclusive primitive for asynchronous use. If multiple tasks update a shared variable such as a global counter, conflicts can occur. By enclosing operations with a lock, you can maintain consistency. Event is used when one task signals that it is ready, and other tasks wait for the signal. This is a simple way for tasks to share signals and synchronize with each other. Event has a Boolean flag, and calling set resumes all waiting tasks. It is useful for simple synchronization. By using Queue, producers, who create data, and consumers, who process data, can coordinate smoothly and asynchronously. Also, when the queue is full, producers automatically wait, naturally implementing back pressure to prevent overproduction. Queue helps coordinate producers and consumers asynchronously. Additionally, setting max size makes the producer wait on put when the queue is full, preventing overproduction. For CPU-intensive processing or when using libraries that do not support async, use run in executor to delegate processing to another thread or process. Doing this prevents the main event loop from stopping, allowing other asynchronous tasks to run smoothly. Calling synchronous functions directly will block the event loop. With run in executor, the code runs in a separate thread and asynchronous tasks can continue to progress concurrently. The following is a sample scenario where API calls are rate limited and heavy processing is performed on the results. Combining Semaphore and run in executor allows processing to proceed safely and efficiently. We use a semaphore to limit the number of concurrent API calls, and heavy processing on the resulting data is delegated to a thread pool. Separating network and CPU processing improves efficiency. When a task is cancelled, properly handling, finally, and asyncio cancelled error is very important. This ensures files and connections are released and intermediate states are properly handled, maintaining consistency in the application. Cancellation is delivered as an exception, cancelled error, so perform necessary cleanup in the except block and re-raise the exception if needed. The following are practical points useful for designing asynchronous processing. Explicitly control concurrency. When there are resource limits such as APIs or DBs, you can limit the number of concurrent executions with semaphore. Handle shared resources safely. If you need to update state from multiple tasks, use lock. Reducing shared state and designing around immutable data makes things safer. Choose how to receive results. If you want to process tasks as they complete, use asyncio.as_completed. If you want to process results in input order, use gather. Isolate heavy synchronous processing. For CPU-intensive or synchronous library calls, use run in executor or process pool executor to avoid blocking the event loop. Plan for cancellation and exceptions. Write proper exception handling to safely clean up resources even if a task is cancelled midway. Make testing easy. Abstract side effects like I/O, time, and randomness so they can be replaced, making it easier to test asynchronous code. Asyncio is powerful, but if you focus only on running things in parallel, you may encounter issues such as shared resource contention, resource limit violations, or event loop blocking. By combining semaphore, lock, event, queue, run and executor, and proper cancellation handling, you can design safe and efficient asynchronous applications. By utilizing mechanisms such as the producer-consumer pattern, concurrency limitation, or separating asynchronous and blocking processing, asynchronous workflows can be constructed more safely and efficiently. The source code for this video can be downloaded from the official website. If you like, please visit the URL in the description to aid your learning. Thank you for watching until the end. Please subscribe to the channel and look forward to the next video.